My name is Sarah Fink. I'm the Community Manager here at 3D Hills. And so our agenda for today, firstly I'm going to have Professor Ivan Cole come up and give you a bit of an introduction above and beyond the tour as to what's going on here at RMIT. And then we're going to have 4 presenters today. So we have a breadth of knowledge from research, industry, startup, bioprinting and metal printing, whole polymers, with a whole range. So I'll start from myself and a bit about the community 3D Hills. So 3D Hills is really a community about 3D printing healthcare, bringing together innovators, startups, research industry, and bringing people like ourselves all together to the one place. It's about education and collaboration with a real focus on startups and innovation. This group was initially founded by a lady in San Francisco called Jenny, and it's now grown to a number of cities worldwide, 20 plus communities and more coming each month. So a little bit about myself and why I came to where I am today. So I'm a biomedical engineer. I work at a medical device startup called Olmec Solutions. So we work on customized and 3D printed maxillofacial implants. In particular, this TMJ prosthesis is what I work on, and it's a jaw joint replacement that's customized to the patient. I'm also a co-founder of a startup called Swade MedTech, working in a bit of a different medical space in these thinking of patients, but we also use 3D printing in our prototyping and product development. So I actually came across 3D Hills when I went to their conference last year. They have a global conference on 3D printing in healthcare, as well as satellite events in the communities like this one today. So this is obviously this year's event, which has already been, but there will be future events for the global community if anyone's interested in travelling to the global summit. And recently there's been a focus on startups and supporting and growing new companies, either here or abroad. So at the moment, they've held a Pitch 3D event in Boston. I think they've had one recently, or they're holding one soon in Spain. So this is something that we may look to hold here in Australia. So if those people involved with startups or connected to startups, please let me know about what's going on in Melbourne. If you know of companies that would be interested in this sort of event to connect up startups with supporters, researchers, and as well as investors. As you can see, there's a number of events, including this one here today, going on around the world. And a little bit closer to home, these are not 3D Hills events, but these are some events going on within the community. So at BioFab, where one of our speakers works, they currently have a performance, so a theatre performance going on in the lab. And also Jason, one of our speakers, is running a 3D Med conference in, I believe it's 14th of October. So just some other events that will be going on in the future. And we can give you more information about these events, because obviously the slide will move on, we can give you the links and things like that if you're interested. So now I'm going to hand over to Dr. Ivan Cole.
Thank you. Sure I can get it there. Perfect. Thank you very much. Firstly, let me, on behalf of RMIT, say how glad we are to host 3D Hills. We certainly want to encourage the growth of the industry and have been working on it, particularly through Professor Grant for, not sure how long, around a decade or
Nearly decade on.
a decade on pushing additive and its application to implants. But Milan's work is excellent and having a lot of impact, but there's quite a few other things happening as well, which I quickly want to take you through in the next 15 minutes. Just firstly, a little bit about how RMIT has organised its research. I won't go into this in a great deal of depth, but I'll touch on it. RMIT has decided it wants to make its research impact much more effective, and so it's focusing its research in 8 areas, only 4 of which I will mention today for shortness of time. Advanced manufacturing and fabrication, which I lead that platform. These are platforms. We're not the boss of any of them. We try to coordinate and facilitate research in particular areas. Rachel Crusoe, who's sitting in the audience here, it's the area on advanced materials. We have an area on biomedical health and innovation with Magdalena, Levatsky, and obviously these three areas work very closely together, particularly in the implant and additive space. And then we have a series of others which we won't go into. By advanced materials, ECP, aim is to bring together experts, participants at RMIT to build, develop and grow industry links, harness their expertise and facilitating industry engagement and impact. And it's focused on 6 core areas, which for the sake of it, I left that. Advanced materials is to build advanced manufacturing and fabrication industry that provides integrated customized services for objects. So we want to go past just the object to the service, which is exactly where implants fit in. The biomedical and health innovation, ECP, is looking at critical areas of ageing, population and urbanisation. That leads on to the particular diseases and conditions associated with those events. And to do that, understanding personalised medicine, bedside medicine, lifestyle, vaccine and drugs. So that's how we're implementing our research going forward at RMIT. There's been now talk about the areas associated with implants and generally additive manufacturing for biomedical applications. So what structures do we have? We have an ARC training centre in Additive led by Milan, which brings together bioprinters, biolinks, clinical tools. Should be additive bio, I think there's a word dropped off there. We also have our Centre for Additive Manufacturing, which is also led by Milan, and you've been walking around it. We are now a partner with Swinburne and other institutions in SEAM. It's only about 1 week old. Service enhanced additive manufacturing. So they're the 3, I guess, institutional structures that help us do our work. What work are we doing? Obviously, major focus on metallic implants, which you've just seen as you toured. Starting, this probably answers the question of, this is Milan's work from 215 with the first 3D printed spinal implant produced by Atomics, and with a very nice design shape and getting the maximum strength from that complex shape. That sort of work still goes on well and is carried downstairs, but Milan's new driver is how do you make implants just in time? How can you produce the implant just when the patient needs it, just after you've done the surgery? So the major program is Striker at the moment, working out how to do that, how to design it, and how to get that high throughput work done. We do a lot of work on titanium and a lot of different titanium alloys. We're also looking at new alloys for orthopedic and dental application. Zirconium is one of them. This is work done by Mark Quinn. Going out of the structural implants, we do a lot of work on metallic scaffolds. This is work done by Cooley Rad, looking at particular structures, particular geometries, and how we could design those geometries to give us enhanced manufacturability, strong biocompatibility, and a combination of biomedical topography processes. These are more titanium, biocompatible titanium alloys, and the novelty is in the innovative structures that she's developing. 2 or 3 groups working on surface engineering for implants. Work done by Kate Fox, looking at diamond-coated titanium skeletons and seeing if you could get stronger biocompatibility with diamond coatings. And the initial results indicates that you probably can. Work done here by my colleague Zalbo, which is looking at how with strontium coatings we can change the balance between my pronunciation of medical terms is not great, oculoblast and oculoclast, change that balance depending on the nature of the coating to give better biocompatibility. Work done by my own team in conjunction with Cyro, looking at cold spray titanium tantalum coatings. The particular advantage of the cold spray of this is we actually do get particles of tantalum in the coating, and the hope is that those titanium, those tantalum particles will promote better biocompatibility by allowing stronger cell growth on the tantalum. But it's not all about metallic work. There's also quite a lot of work on looking for scaffolds for cell graft. This work is done by Richard Williams. A lot of work looking at peptide-inspired structures, looking at microscale scaffolds for stem cells, looking at cross-link nanostructures for stem cell growth, and looking at if we can transplant those structures with the stem cells into the brain and promote neural regeneration. So that's just a very quick overview of some of the work done at RMIT. So we're going from the metallic areas to new metallic structures to actually use surface treatments of those structures to looking at scaffolding for stem cells. And there's more work that I didn't have time to cover in that quick 10 minutes. So very happy to chat to anybody, very happy also to follow our many inquiries to particular professors whose work I've highlighted. Once again, delighted to have you here, delighted to support 3D Heroes, and hope this will be part of the growth of our community. Thank you very much.
So next up, one of our 4 presenters, we have Jason Chen. Jason is Director of Vascular Surgery at Austin Health. He also heads the University of Melbourne Medical 3D Printing Lab, also known as 3D Med Lab. He completed his specialist training in 2007 and has held multiple governance roles, including Victorian Chair of the Royal Australasian College of Surgeons, AMA Victorian State Councillor, and President of the Australian Chinese Medical Association of Victoria. He has a passion for medical innovation technology and maintains multiple active surgical research streams. Please welcome Jason.
So my apologies if I can't outdo my work. It's very impressive, the facilities here. And if you ever get a chance to come and visit my lab, I can promise you'll be sorely disappointed.
There's just a receptor if you need them.
Okay, we're all there. So what I was going to talk about, and feel free to shut me up if I'm going on for too long, Sarah, is just a very quick run through of the type of applications that we're seeing and we're using 3D printing for in additive manufacturing in medicine and surgery. And thank you once again to Sarah for promoting our conference, which is in October. I do have some flyers here, but you can only have one if you promise to put it up somewhere everyone else will see it. Otherwise, if you do need to contact me, I don't hand out business cards these days, but you can easily contact me on social media or by Google. It's very scary when you Google yourself and find all sorts of things you didn't want to know. So one of the things I'll point out is that medicine and surgery is a very complex environment, and there is a lot going on in the middle of an operation. The amount of equipment and tools that we use is all over the place. It can really do your head in as a nurse trying to keep track of all of this equipment here. But thankfully, most of the time we have a plan for what we're going to do, even though it's sometimes relegated to the corner of the room over there. But 3D printing is sort of one of these things that was very abstract and we really couldn't work out where it would fit in. But our anaesthetists, despite them having lots of fun playing with all sorts of new medical technology, they were probably one of the first groups that I managed to convince to work together with us to find applications for it. The talk is about sort of whether it's a passing fad or the future, but essentially I wanted to make sure that we were talking about the right type of fad. These are sort of things that came to my mind. My son tried to explain this to me, and I still don't get it, so if anyone can do that, then please go ahead. it's no surprise to most of you. I think most of you have some knowledge and interest in 3D printing already, so you know that it's been around for quite a long time, and that it's in use in lots of other technologies. But the thing is that if you look at why it hasn't taken off in medicine, and this is really what got me interested, was that for something that you heard quite routinely in the aerospace industry, or other forms of the sort of advanced engineering, no one talked about it in hospitals, no one talked about it in terms of applications. And a lot of it, I thought, was really just ignorance. So as doctors, we thought we knew what we were doing. We didn't really feel like we wanted the world to change. Everything as a surgeon is all about my level of skill, rather than what other things I can adapt and bring to my work. But this field is really completely dependent upon other people. It's about acquiring good quality imaging if we're going to make anything that's related to anatomy. And that's something that I personally cannot do. I have to rely on someone else to acquire that imaging. It relies on being able to process and post-process that imaging to something that is printable or something that is useful. And again, that's a skill that I don't have. It's something that I have to either learn or I have to get someone else who's trained in this. And it's also very dependent upon the type of materials and the restrictions that we can have. That's why the work that Ivan does here is so important, that we need to have a range of materials that serve the applications that we have, that we need them for. So one of the things that we do, similar to the lines of this 3D Heals movement by Jenny Chen, who's a radiologist and works in this imaging space, is to make sure that doctors and technicians can communicate with each other and understand what it is that they need and they can supply, so that we get these collaborative experiences. And that's what these training workshops that we run are all about. So, as I said, my lab is very under-equipped compared to what you've all just seen downstairs. We had two of these, and now one's on the blink. And this last one's on its last legs, and this was our last toy that arrived last week. But they are far from being able to produce a magical organ or a soft tissue structure like you might see on Star Trek. But when we've got a tool, as they say, when you've got a hammer, everything looks like a nail. So we've been busy trying to print everything that we can get our hands on. This is some of our work in action, but the number of technologies in the field is growing all the time. One of the things we're really interested in is not just what can you do with it, but how do you study it? How do you put it in a context that other people can learn from it? And so we've been keeping an eye on the publication rates of papers in medical application of 3D printing, and this is where things really, really took off. But interestingly, you look at the type of publications that are coming out, regenerative medicine, which really falls into that tissue engineering and cell culture bioprinting space. And if you really look at it, the vast majority of those papers were not really technical papers. They weren't really demonstrating anything. They were really speculative papers, talking about what we could do or what we wish we could do. And so despite this sort of large volume in papers talking about what we'd like to do, there is very little papers explaining to people how to do it. And if we look in just the vascular surgery field, so I'm a vascular surgeon and I operate on blood vessels, again you see this big rise in the number of publications, and I have to say that I'm responsible for about that much of it. But it is mostly sort of one-off things, so it's people going, look at what I can do, not what I can show you how to do. When we look at the type of applications that we have access to, so my lab personally does not do any bioprinting because we don't have the resources for that. It's quite complex and it's a very long lead time, and there's no way that I can scrounge up that time for that capacity. But what we primarily work on are things that are visualization, or things that are used for design or planning, along the pathway of things like Sarah was talking about with titanium jewels and medical implants, but not towards the final end of that scale. But more about sort of helping doctors and surgeons decide when is the right time to do that kind of work. And we also work very much on simulation and models for teaching and training. So things like teaching people how to manage wounds, teaching them how to put in screws and plates, how to make an incision, and how to plan an operation, or for a particular operation, how to do that specific operation, or in that particular patient when the anatomy is rather unusual. This is the sort of other end of making actual implants, and this is the kind of higher end work that Ivan and his group and Paul Durso is involved in, and is probably where all the money is, to be honest, which is no surprise when you see where the grants are being allocated. So what we do is simple but cheap but effective. Things like making models so that you can see an artery. So this is a carotid artery where we can demonstrate this sort of loop-the-loop, which adds a layer of difficulty to surgery for a vascular surgeon. And the relationships between abnormal vessels. So this should be a single blood vessel around here, but this is what we call an aortic ring, where the main aorta, the main blood vessel coming out of the heart, is wrapped around this tracheal structure. When you're doing anatomical modelling, we have to look at a lot of factors, and to be honest, we're not really very good at this. It's something that we really need to become more organised in. But understanding how correct our segmentation is, that we're making models that represent what it is that we're seeing, that the dimensional accuracy is close enough. That depends on the application that you use. So if what you're doing is just having a look at something, it doesn't matter if it's a couple of millimetres off. But if you're actually planning an implant of this, then it does matter. And things like rigidity and materials behaviour is important if you're going to be touching it and trying to do things to it, like make it pretend to be tissue for a simulation or a teaching exercise. So we have to look at all of these issues when we're deciding which technique to use to create a particular model. So just some very brief run-throughs of the kind of applications. We can now take a CT scan like this and segment it and then produce a model like this, which is used for teaching, so that people can start to identify and understand the relationships between blood vessels. These are models that we make prior to surgery, so that surgeons can look at this and say, well, this is something that I can operate on, or this is too difficult, or I need to change my technique in order to do that. Heart valves, livers, kidneys. This is a kidney with a big tumour on it, and it's specifically made to show the blood vessels so that the surgeon can work out how to cut out the cancer whilst preserving as much kidney tissue as possible without cutting through these blood vessels. We're making hollow models that we can put stents through and deploy so that we know how those stents are going to behave in a real human. And we can have models where we use them to cut out a stent, so you might take a pre-existing stent and then modify it based on a template. And this is a model that we've made and put under an X-ray fluoroscope, and then actually practice passing wires and catheters down to make sure that it behaves the way that we want it to behave. So my trainees were very excited when they did that, and it's pretty rudimentary what we do, but as long as we get the results in terms of experience and teaching, then it does the job. These are some of the other things that you'll see. So this is the next implant from George and these are sort of sample hip joints and things, but they're all often conceptual. But there are a lot of advances in this space, and I mentioned before about coatings and different materials on top of a personalised device. And there was a fantastic speaker, I can't remember her name, but she came out from the US recently talking about ionized coatings, where you can actually get different layers of drugs onto an implant so that they're released at certain time periods. And those drugs can stimulate cell growth in certain manners, or they can have antibiotics released at the right time in that patient's healing process. This was the template that I mentioned before that we place a stent into so that we can cut holes out for the branches and make sure that it fits the patient that we're going to operate on. We downstairs, we mentioned before about making models for simulation and the University of Rochester's Mayo Clinic experience. And these are the types of models that we can make, but to make that whole thing out of one 3D printed process is not workable. The range of material, the range of textures that you have to produce is too difficult. It's a very expensive process and very slow, especially if you're going to plonk it in front of someone and have them cut it up and then it's gone. So you have to be inventive in terms of which parts you print, which parts you mould, which parts you cast, and which parts you use more expensive materials for, and which parts you use simple materials for. This whole just-in-time concept is a big deal. This is the process that a medical implant goes through. So you have to manufacture it. There has to be someone who goes through the regulatory process to get it into your country. It has to be brought into the country, it has to be stored, it has to be shipped to your hospital, and then the surgeon actually puts it into the patient, and then the bits that you don't use or wasted then get disposed of. And there's a long pathway from this factory to the patient. And what happens in a typical hospital, this will be seem very familiar to Paul, is that every day we get these crates of materials of screws and plates, wires and tools and implants shipped to our hospital. And then inevitably we use probably about one box of these. We open about 10 of them and then take out one piece from each one so they're right size, and then we ship them all back. And then the next day we get a whole new shipment. And this is a huge waste on resources of transport, fuel, energy. So what we want to do with this just-in-time manufacturing concept is, if you know what you want, then the night before or the week before that patient's going to have surgery, it doesn't even need to be personalised. It might just be that you have a bank of models in your computer software, or you might order it from the company online, and they'll send in the plans and then print it in your manufacturing room in your hospital. And it might be a standard product that you no longer have to ship, or it might be something that's completely personalised to that patient. But you can now move that manufacturing facility from an overseas company to your hospital and make that whole process a lot faster and a lot simpler. I was having a discussion earlier today about what's possible and what's not possible. There is a lot of work on making things 3D printed that look right, but that doesn't mean that they behave right. So just because you can 3D print a stent that looks like a stent does not mean it has the mechanical properties of a self-expanding stent. And essentially, this looks great, but there's no way that we could ever put it into someone or for it to do anything useful. But we'll get there. Bioprinting I'll leave. I won't cover that because there's plenty of opportunity later. But this is the really big issue, is if we change manufacturing to these one-off small batch processes, and each object that you create is no longer in volume, so you can't take a whole bunch of them and test them for strain and strength and wear and tear, but you have to rely on your design being, and your materials being over-engineered to handle what it is you want to throw at it in terms of mechanical forces, or quality, because it might be as simple as being adequately sterilisable or not having material faults in it. How do you change the regulatory process from producing an object that again gets tested to ensuring that the manufacturing process is the thing that's regulated? And Paul will have a lot to say about that, I'm sure.
There are obviously lots of things that are just cool. I don't think this is really very practical, but nevertheless, I think this group managed to get $1 million out of Google, so there's obviously a lot. So as I said, our lab is very, very small, and it was founded based on very limited resources. Pretty much everything I had to get out of my own pocket. But this is sort of what we aim towards, is a facility perhaps not as impressive as this, but enough to serve the purposes of a standard hospital, and which is integrated in with its other departments. So we've had a lot of discussions over whether a 3D printing facility should be on-site or off-site. My real belief is it should be on-site, and it should be something that a doctor can walk into and say, that looks great, I want one of those, can you do this? That's not quite working out, let's change our tack. Or similarly, an engineer can come and hang out in the operating theatre, or come and visit us and have a talk about, I've got this new technique, how can we try this out or find a way to make it useful. So that's what I would like to see, but I realise that the resourcing and capital issues don't really make that possible. This is another one of our partners in Toronto, and we have another group in Poland that we work with that we exchange tips and ideas. So is it a fad? I certainly hope not. I think it's something that's here to stay. But some of the hype that is being put forward is not realistic. And I think part of the reason why we need to be here to collaborate with each other is to work out what is realistic, what is really achievable, and how do we make sure that we get those things done. I put this up really just to say that engineers and clinicians can work. It may be ugly. I'll let you guess. And just in terms of the meetings that we run, this 3D Heals event, we've been running 3D printing and 3D manufacturing and 3D visualization related conferences for the last few years. Come along to our event in October, but more importantly, you've got 2 weeks left to submit an abstract. So we have come to an arrangement with a medical 3D printing journal to have accepted abstracts published. So it's a really fantastic opportunity for you to present your work, have it indexed and citable, so that we can develop that documentation and share that knowledge. The sort of hackathon concept is something that's really taking off. So this was one that we ran in 2016 at Melbourne Uni, and I think it's since been absorbed into the Graham Clark Institute each night. So we want this event to grow. We want you guys to be able to connect and talk to each other. So please, please, please come and check out our resources and come and visit our meeting and submit some abstracts so that you can share that with everyone else. Yeah, we can hand them around. So I've brought along some models that we have printed so that you can see. And this really reflects the kind of work, the kind of work that's done downstairs as well. I didn't bring along any metal 3D printed parts, but these, for example, come from those photopolymer or polyjetting printers downstairs. This is an aortic valve that's printed on an FDM printer, so like the Zortrax and the Maker bots that you see downstairs. And this is a carotid model on the same sort of thing. And those are with rigid plastics, rigid thermoplastics like ABS or PLA, but they do come in flexible plastics as well. And you saw the SLA printers downstairs, the UV photo curing ones. And these are the types of models, these are tracheas that we've printed, which we use to train our anaesthetists how to perform bronchoscopy or to do percutaneous tracheostomy, which is where you put the needle into the trachea and then pass a tube down to help people breathe in an emergency.
Thank you. In the interest of time, we might just move straight on to the next speaker. We will have a chance for discussion with all the students at the end and answer some of your questions. So next we have Paul Verso. Paul is an Australian neurosurgeon, founder and executive chairman at Anatomics, a Melbourne-based company. His unique experience in research, clinical practice, teaching, commercialisation, and medico-legal opinion has made him an internationally recognised Australian neurosurgeon, scientist, and innovator. He invented the technology of biomodelling with groundbreaking PhD research, and as I said, founded Anatomics. Paul was a fellow at the Cambridge University Neurosurgery Unit and a clerk at Harvard Medical School. He's published and presented numerous papers, holds multiple international patents, and has numerous research prizes. Please ignore welcome.
Thank you, Sarah. Thank you, Ivan, for hosting us here tonight. And thank you, Jason, for a great talk. And Jason's done a great job with very little resources to build a lab out of nothing, which is fantastic. And, I wish there was another 1,000 surgeons like Jason who would step up and help us with this great work, because it's definitely the future, I think, in what we're going to be doing more and more about medical applications. And I think the last slide, or this, one of the last slides that Jason showed of the cat and the dog together, I mean, that is the future. And I'd imagine who's an engineer or wants to do engineering or CAD or design or that sort of work in this room? Right, well, I guess you're all the cats, okay, that are going to come and love you. Vicious hound here who's going to be in the operating theatre. But more and more doctors are going to have to become like engineers, and I think engineers in the medical world will have to become thinking more like doctors and coming together. So I'm going to take you on a little journey of mine, and I've sort of called this community-based personalised healthcare, because I think this is probably going to be our future in a lot of different applications with rapid prototyping. And you might think this is a recent photo, but in fact this is a photo that was taken when I was doing my PhD. And I started my work in 1991, and at that point, Australia's first 3D printer came from the United States. It was a machine that Chuck Hull first commercialised called SLA 250. And that machine came along, and I thought, well, there's a 3D printer. At that time, computers were just getting to a point where we could actually render a CT scan. And in those days, it was a big deal, like a 486 computer. Wow, you know, that was pretty cool. A DX33, or you know, that was kind of the top of the line PC that you could get, with like a hard drive of 40 meg and a RAM of 1 megabyte or something like that. So my idea was to get a 3D printer and a CT scanner and join them together. I came up with this concept of getting a CT scan, creating a 3D data set, and then 3D printing it and creating a model. And I got a grant for $1,200 from the hospital. And after about a year or two, eventually we managed to do this, which was sort of a huge amount of work that had gone into just making the very first one. And I didn't have much money to spend. In fact, I had a very small amount of money from the hospital, and I thought, well, I'm going to spend that money on something that's really worthwhile. I'm not going to blow this on something that's kind of a crappy case or someone who doesn't deserve it. And this little girl came through Uniplast, which is a charity arm of the College of Surgeons that brings kids from the Pacific Islands for reconstructive surgery. And she had a condition called a frontonasal encephalocele. She came from the Solomon Islands, which is a very disadvantaged little place. It's got great diving and terrible malaria if you want to go there. But she came along, and I thought, well, this child deserves, this is the perfect patient for me. So we 3D printed her skull. And this is the first child in the world that ever had a model made. And with that model, it's kind of crude, it had 3mm slices, and it was done on an old-fashioned scanner, and it had a reel-to-reel tape. We made that model, but her mum came out with her, and I was able to show her what was wrong. And for the first time, we could hold someone's skull in our hands and look at it before we actually cracked the head open, have properly, right? And I think that really got me, and I think you can see that the change in that kid's life was so huge that I knew that I wanted to do two things with my life. One was I wanted to be a neurosurgeon so I could do this as well. And the second thing I thought is, well, I'm going to follow up with 3D printing and follow this through and see where it goes. And at that point, I moved on, and the word spread down to Melbourne. And this little boy came from the Philippines, again through Interplast. And this time I thought, well, let's make two models. So this time, the surgeon who was Tony Holmes at the Children's Hospital could actually get a model and reconstruct and simulate the operation before actually doing it, right? And so he got the model and cut it up, and he had one for reference and one as a reconstructed model, simulated the surgery, figured out a way to do this that was even better than what we were doing before, and created a new surgical technique to correct this deformity. And you can again see the outstanding type of result we got. And this is the first child in the world that ever had a model made of their skull, had a surgery simulated, and then the surgery was executed. And with this type of technique, we can have one model, which was a reference model, and they can be dissecting away. And the other model could be used on a side bench to actually get bits of bone and put it together again and reconstruct. So you can have simultaneous surgery occurring, and the team could split into two with the two models and work on the operation and reduce the operative time. So in the research then, I started doing more and more neurosurgery as I was doing my PhD, and this sort of problem is a common issue we see in neurosurgery. And if people have a stroke or trauma, their brain swells, we take out part of the skull to let the brain swell, okay? And often that will save the patient's life. It reduces the intracranial pressure, but it leaves you with a big hole in your head, right? And sometimes the bit of bone's sort of got tarmac and gravel on it from the roadside. You have to chuck it in the bin. Sometimes you put it in the fridge and someone pulls out the power outlet and it defrosts, and you can't put the bit of bone back. So what we typically do in this situation is called a cranioplasty, and we get cold cure cement, like you bog up your dent in your car, and you get this stuff and you mix it together, and it's quite aromatic in the operating theatre, and sort of goes off and everyone gets high on the vapour of the stuff, and it gets really hot. And then what we do is we bog it into the hole, and bog up the hole in the person's head with this bone cement, and it's steam, it's exothermic, and we put water on it and so forth, right? And I thought, well, maybe if we make a model of the skull, we can make an implant prefabricated before we go into the reconstruction. And so this is a prefabricated acrylic thermally polymerized implant, and we put the first one in about 1993. And after I finished my PhD, then these implants were sort of in demand, right? Surgeons could immediately see that this was better than bogging it up, or at least some surgeons could see that, right? So that created, and there was no randomized prospective double-blinded trial on this sort of stuff. It was like, well, obviously it works, let's just keep using it. And so as a result, I set up Anatomics. And Anatomics then has manufactured these type of devices out of different materials, which are acrylic, titanium, and porous polyethylene. And we created a nice little cottage business, which was making this stuff for neurosurgeons in Australia. And then I went off and became a neurosurgeon, and I had 4 kids and do all the other stuff that you do. And this little company ticked over. And that was like, I think you saw the graph of the publications, it's kind of flat lines for ages, and eventually it started picking up. Well, there was a lot of flat lining going on in the development over 20 years with this, but now it's sort of starting to pick up. And so I guess this case popped up to Anatomics a couple of years ago now. This guy had a tumour in his sternum, and there was no way of reconstructing this problem. By cutting out the tumour, you miss your sternum and the rib cage is a big bloody hole. And you're back to bogging it up, right, with cold cure cement and bits of wire and trying to make it up on the go. Spanish cardiac thoracic surgeon said, can you guys make us a rib cage? And we're kind of dealing with a lot of the worst things that no one wants to touch, basically, and that's where we sort of created our little niche in the medical device world. And I said, sure, we'll do that, not a problem. So we printed out the rib cage and popped it in, and next thing you know, Mr. Turnbull's announcing out his, innovation agenda, $1 billion, holding our rib cage up, saying how terrific Australian innovation was. Haven't heard that much since then, but it sort of got the CSIRO in the headlines. Everyone was pretty happy with that. So we iterated on it, just like we iterated on the kid with the frontonasal and campylocele. And I thought, well, gee, what's the next thing we can do? This kind of sternum was a bit heavy. Okay, and this is one of the great things about custom manufacturing is that every person is different, right? No 2 people are the same. And so the next one you can make a bit better than the last one, right? So it's kind of iterative and self-improving. And so this sternum's kind of a bit heavy. Wasn't quite right for that person, but better than bogging it up with cement, right? So then I thought, well, okay, let's do a composite implant. This time we created an implant that contained titanium substructure, which is 3D printed. But then we created a porous polyethylene. Porous polyethylene is a plastic material which the CSIRO helped us develop, which is great, and it makes it very lightweight. It reduces the weight of the implant, and it also allows modification during the surgery by the surgeon. So you can carve into the stuff, you can stitch into it, and it also allows tissue integration. So the muscle or the soft tissue can actually grow into the pore star and create an integrated implant, and the titanium's there for the strength of the substructure. And so the beautiful thing about this type of technology is it's iterative, and you can machine it, and as you do more of these types of cases, you get smarter and better at doing it, because you're always feeding back into it. Now, Jason touched on this, but this is our paradigm at the moment in surgery. It's called a smorgasbord, okay? And so I turn up to the operating theatre, or my colleagues turn up to the operating theatre and say, what are we doing today, right? And I might shock you with some of these things I'm going to say, but I know you're all friends and you're kind of learning about surgery and what really happens. But what are we doing today? Oh, doctor, we've got a hip implant. Oh, terrific, hip. Which side is it? Right, great. Okay, right. And in that room, you've got all this stuff, right? You've got every size of hip implant. There might be 10 different sizes. You've got all of the equipment. You've got reps. You've got X-ray people. You've got all of this stuff there for the surgeon, because I'm the surgeon. I need to have all that stuff ready. Please, thank you. And all of this stuff's there, right? And then the surgeon turns up. What are we doing, right? Okay. Oh, hip implant. Oh, okay. And so you only want, like off the smorgasbord, a croissant and an apple and a cup of coffee and, chocolate or something, right? And then all that stuff goes in the bin. Waste. Okay, all that stuff's sterilised, counted, processed, and it goes through this ridiculously labour-intensive effort. You get all that smorgasbord ready, like out in the kitchen, out the back, mixing up everything, getting it all ready, cutting the tomatoes, the lettuce. It's all there, right? And I'll just demonstrate the way that this paradigm that we're in at the moment of mass manufacturing, delivering lots of stuff, having a smorgasbord, how all this can change with this type of new paradigm of 3D printing or additive manufacturing and planning and all the sorts of things that I think you'd be interested to know about. So this is a patient who turned up to see me, and she had a really painful joint right at the top of her spine at C12. Okay, and now C12 is kind of a tricky place to operate for us as neurosurgeons, because in the middle of your spinal cord, if you put a screw through that, they're basically either dead or locked in. And either side of that is the vertebral artery. And if you hit that, then you can have a stroke. Okay, and the screw's got to go kind of right between all of this in exactly the right place to fuse the joint. And this lady was terrible. She couldn't move her neck. She couldn't drive a car. Doctor, I can't live like this. I want to die. Please do whatever you have to do. And I said, okay. So I said to the company that I would have normally worked with, bring all your stuff for a C12 fusion so I can see what you got for the case, And these are all the drill guides. And these are more drill guides and drills. And these are all little screws that we put into the neck. Okay, we're going to have all the different sizes and lengths and diameters, and each one of them is worth $1,500, and they're in a caddy. And then we have all the little rods and connectors and plates. And then we have more widgets and rods and things, and benders and distractors, and more instruments. And then the company who makes all this junk says, doctor, you've got to have the computer navigation system so you get the screw in the right place. And so then we have a navigation system, and fancy software, intraoperative scanner to scan the patient. And everyone has to run out of the operating theatre and you nuke the patient with the scanner and you wrap them up like a sausage and you come back in and it's got the data for it. Cool, $1 million of equipment. And that also comes with more sterilised requirements, right? So this is the smorgasbord, okay? And I think Jason showed it very nicely. And this is the inventory that can't fit in the storeroom because it's all in the foyer where the lift goes at the hospital, and there's so much junk here going on. This is the guy that has to deliver all this stuff, right? Pushing trolleys. There's a nurse taking the stuff into the operating theatre to be sterilised. And this is like the back of the kitchen, the goods and delivery part of the smorgasbord that goes on. And inside the operating theatre, it's all sterilised and wrapped in Kim wrap, which is this extravagant wrap. You think plastic bags at the supermarket are a problem. You should see this Kim wrap, how much of this stuff's produced, right? Everything's there on the shelf, all the smorgasbord ready to eat, right? And at the back is all of this stuff, garbage. It's medical waste, toxic, has to be decontaminated. Piles and piles of rubbish and waste. Now, we can't afford this in healthcare any longer. We've got a wasteful system, we've got an ageing population, we're running out of money, no one wants to pay more for their private health insurance, public hospitals got a waiting list, we can't afford it, right? So this is what I did for my patient who had the C12 joint problem. I call it IKEA surgery. Okay? This is what I required. 1 custom implant, 5 screws and a drill guide. And there it is in the model of the patient. And that's it. That's what nurses got to count. Instead of counting every widget and gadget and so forth and that whole set of instruments, this is all we need. What? I planned an operation and I manufactured what I required just in time. And here I am, that's the drill guide on the spine. Checking it to make sure it doesn't hit the vertebral artery. Cool, that's good. Okay. And validating it works. And here's the drill guide on the patient. And here's the implant. Pop it in and put the screws in. It's that easy. Every screw is pre-measured. And I'm just using standard X-ray in the operating theatre, not a fancy CT scanner or anything fancy. You can see how long those screws are, can't you? They're kind of 45 millimetres long. And you can stick one of them pretty much anywhere if you try hard. There's the post-op CT scan. So what I'll touch on now is the new paradigm of where we're going and a bit of science for all the purists in the room, right? This is a normative distribution, and this is what we put biological structures and things into, right? A normative distribution. You've probably heard about it, okay? And then what we do in the medical device industry is we segment that normative distribution into different sizes, right? Because you can't make something for everybody. You have to, make it easy. Then we've got the pygmies and we've got the giants, right? We've got the kind of little people and the really big ones. And they're the ones that live here, at the edges of the bell curve, right? And that's where anatomics has survived and had its little niche and has gathered its nuts and eaten them in the forest. And the big, massive multinational corporations have segmented everyone into those sizes. Okay. Small, medium, and large. And what happens if you have a hip implant? Doctor measures it on the table with your hip open, bleeding. It says it's size 6. Nurse goes to the storeroom, looks there. Oh, bloody hell, we ran out of 6. Comes back, ran out of 6, doctor. What? You ran out of 6? What am I going to do, right? Get the taxi to bring one from Royal Melbourne or St. Vincent's and bring it here straight away. Oh, there's a traffic jam. Oh, shit, I've got another case here. It's the 3rd one on my list, right? What does he do? Does he put bone back to make it a size 5? Oh, put a bit of bone back and pack it in there and put a 5. No. No. You take more out and you make it a 7, right? And the patient walks out of hospital thinking, something's not quite right about this operation. Okay? What's not right about it, right? And they come back and they have a revision operation. Company gets paid twice as much for a revision implant. Everyone's happy. And, and this is what we do now, right? So, this is the future. This is intelligent manufacturing, okay? What we do is we figure out your anatomy, your bone density, and we map and plan all of that out, and we manufacture an implant just for you, your hip, that fits your body, that's built for you, your bone density. And that's the future, because now we can do it, and we can do it here in your lab, Ivan, downstairs. We can make it, and we can make it just for one person, and we can eliminate all of that waste. So all of those crosses you see in this bell curve, that's all the waste we don't need and we can't afford to have any longer in healthcare. That's what it's about. And that's why personalised healthcare changes the paradigm, makes it intelligent, makes it iterative and self-improving, and it creates solutions that are faster, more efficient, and better for patients. But there's obviously some losers in this, isn't there? And I'll let you think about who the losers in this scenario might be. But every person is different, and we can now create surgeon-specific, patient-specific solutions. So if I'm a left-handed surgeon and I'm using a right-handed saw, okay, I don't want to hear that the FDA won't approve a left-handed saw and it's going to take a year to do that and it's going to cost $1 million. Just give me the saw I want. Give me the implant I want. Let me work the way I want to work as a surgeon. Make it surgeon-specific. And make it patient-specific for the individual person. Every person is different. So this is a new paradigm. And we're printing from ranges of materials. We're prototyping biomodels, devices, prosthetics, complex and unique structures. It's customizable. It's iterative. We keep on improving it every time we do it. We create a knowledge base of common sense knowledge that we can share amongst people all around the world to make it better. We reduce waste, eliminate inventory, reduce logistics. It's a lot cleaner to carry it from RMIT to St. Vincent's than it is to ship it or fly it in the 747 across the world, okay? And it's globally disruptive because now we've got distributed manufacturing, but we've got global cloud-based intelligence and design and capability that can be shared by everybody. So what the regulators have to understand is we have to regulate a process. It doesn't matter what the device you make is any longer. As long as that device has gone through a validated, verified process, it's been simulated and tested, the risk is n equals 1. There's one individual person that will either fail or pass with this device. You're not making a hip implant metal on metal that's going to affect 10,000 people for the next 50 years or something like that in our current mass-produced paradigm. So the regulatory has to change. It's not a regulatory system that's going to stay there for 10 years and that implant won't change and you'll make a patented profit for the next 20 years without changing your design. No, it's over. We haven't got time to wait 20 years to change our designs. We've got to iterate this and regulate it and regulate a process, because N equals 1, every person is different, and every device in the future will potentially be different. So process-based quality systems is really important. And the other person that is really important is a surgeon. And if a surgeon like Jason is going to spend time planning his operation, printing out a blood vessel, thinking about what he's going to do before he gets in the operating theatre, that should be rewarded and acknowledged. Because at the moment, the surgeon that turns up and says, "What are we doing today?" doesn't get paid any more or any less than the surgeon that spends a week planning an operation, thinking about what they want to do. That glory all comes within that person, not from the Medicare system or anything like that. We're not incentivised to plan anything at the moment. So our future is hospital-based manufacturing, process-specific quality systems, reimbursement and recognition by government, physician engagement in design and manufacture, surgeon-specific, patient-specific, and online tools and ability to plan and share information, and empowerment of local communities and local people. Jobs for you in this room as you'll be in Melbourne making things for people who live in Melbourne. Okay? And I think jobs in Africa will be for African people, making things for people who live in Africa according to what they want. Enablement is everything. Enable people to make what they want for their own people the way they want to make it. Don't ship things in boxes from America and say, "Eat this crap." You know? There's 6 sizes of hip implant, even though you're this big or you're that big, and that's all you get. Let them do it for themselves, but support them through global cloud-based intelligence. And I think that's the future for healthcare and medical technology. And I'd like to thank you for your time. Thank you.
Next up we have Neil Anderson. Neil is an experienced company executive and biomaterial scientist. He started working with Dr. Chris Hart 5 years ago to develop and commercialise the Additive innovative range of products for the treatment of obstructive sleep apnea, bringing them to market. He's been responsible for managing the collaboration process with Cyro to develop a remotely managed computer-aided detection, imaging and 3D printing manufacturing platform, as well as R&D of their products and manufacturing transfer. Please welcome Neil.
Right, good evening everyone. I'm going to switch tacks a little bit in that these are innovative devices for treating snoring and sleep apnea, much lower class than orthopaedic devices. In fact, in Australia they're class 1 and in the US class 2 as opposed to the class 3s that Paul was referring to. So we're a medical device company. We're listed on the ASX, been listed for the last 2 years. It's really the brainchild of a dentist from Queensland who thought there was a better solution than CPAP for the many people with snoring and sleep apnea problems around the world. The company Aventus was founded around about 5 years ago, and it was really just 2 of us that went on this road to, we hope, is glory. We have about 30 people around the world, mainly in Australia. There's 5 in the US now, and we've just launched our products in the US. So our mission is to be a global leader in the treatment of sleep apnea, which affects 1 million people in Australia, 32 million in the US. If you count China, you're looking at hundreds of millions of people worldwide. It's not just the day-to-day problems that sleep apnea causes. It's obviously long-term health issues around cardiovascular disease, dementia, stroke, and the list goes on. So it's a really important disease to get on top of, and it's probably fair to say there's a number of people in this room with OSA. So the difference with our appliances are that, yes, there's 30 other oral appliances on the market in the US that just pull the mandible or lower jaw forward, helping to clear tongue obstructions, but that's exactly what they do. They only actually prevent obstructions from the tongue only. Those that have other sites of obstruction, such as the nose, soft palate, epiglottis, lateral wall, need and typically treated with CPAP, which is that Darth Vader mask with a reverse cycle vacuum cleaner. 50% non-compliant at 1 year, costs a few $1,000s. Big companies such as ResMed and Philips are making a mozza, but half of their devices that they're sold are being thrown away or sitting in cupboards around the world. So clearly these CPAP actually works, but the patients actually have to use it. Our objective is really to develop innovative technologies that have the compliance of typical oral appliances, which is around 90 to 93%, but have the success rates of CPAP. And you'll see that we're on a pretty aggressive pathway to achieve that objective. So our oral appliances, it's around this airway. When Dr. Hart came to me about 5 years ago, he said, I've made this acrylic device. It took 8 hours to make. It was this big bulky thing. The airway was too small. Our airway really has the requirements of simulating the nasal passage, which is about 50 millimetres squared each. So we decided on 3D printing was a good option, and met Stefan pretty well 5 years to the day, I mentioned to him, and started this journey. So this is the device itself. I just have to make sure I have it.
I think it's a corner of the image is usually on the mouse.
So this is a device, fairly young person actually, so they're asleep. And you see people on trains, buses, or even maybe your partner laying back. Mouth opens, their nasal obstructed, lower jaw drops back, leading to obstructions in that airway. Could start with snoring, but leading to sleep apnea. What our device does, as you'll see, looks very pretty there and polished in this simulation. Air comes in the front and delivered at the back, past the tongue, underneath the soft palate, and obviously acting like a second nose. Great for those nasal obstructors. I'm one of them, around about 40 to 50% of the population. Goes in the patient's mouth, the mandible stabilised in a forward position, and they're able to switch to mouth breathing only when needed. And that's often all the time if a person is in fact nasally obstructed. So that's the device. We've obviously started with 3D printing. Why did we choose 3D printing? First devices with titanium, quite expensive. This is really a consumer good, but we're able to, I suppose, improve on the technology through various iterations. The key thing here is that they're bespoke designs. So we have a 3D printer and it can print at least 20 of these in one layer at a time, all totally different. You have to get the cost down. They are a very complex shape with a convoluted airway, impossible to use traditional manufacturing processes, not only for the individual design, but because they're bespoke. We have a new device coming out in mid-October, which is 3D printed out of nylon. It's a medical grade nylon, but still has the airway. You'll see here, we're actually 3D printing the teeth landing area as well as the airway itself, which is, things around fit of the appliance become much more important as opposed to the other devices where they're just moulded to a dental model for the patient. Titanium was seen as very strong and thin walls, so the titanium devices are about 0.5 millimetres thick and very lightweight, so these devices are in the order of about 20 grams. The nylon one is around about 1 to 1.2 millimetres thick and obviously much lighter weight. We also make a lot more money out of this. The cost of goods sold is significantly less than the titanium ones, and I think it's fair to say initial feedback is, especially from females, that they see that lighter, white device is actually more user-friendly, if you like, than the titanium ones. And of course, it has to be biocompatible. relatively low cost of sales. I mean, any medical device company has to come up with a product where you're making at least 75% margin, otherwise you cannot compete. That's the golden rule in medical device design and manufacturing to be able to compete worldwide. So these are devices that sell for around about $700. So if you look at our COGS, our objective is to get that in at under $200, which we can do with the nylon. It's difficult to do with the titanium one. So where is 3D printing used? It did start off as a proof of concept prototyping. I had to dig this very old picture out. This was a very early prototype, probably 2015, printed on the A2 printer in Lab 22 at the CSIRO, probably 2014. So yeah, we needed to do a proof of concept. The advantage of being a low-class device is that we can try it on ourselves at pretty low risk. Obviously very difficult to do with implants. The next stage for us was to then design and develop the device once we completed that proof of concept, introducing, I suppose, other aspects for comfort and making it more user-friendly, better appearance, and then eventually we also moved to using 3D printing for manufacturing. But I think it's fair to say 3D printing has a role to play in all three of those areas. It just so happened Aventus has used 3D printing for all three of those. We've also, if you like, we have new products actually coming out in about 2 months' time. The first one is the X-Bend. So what does this do? So if you look at mandibular advancement, has alone, so that's just putting the lower jaw forward, a la Somnomed, other companies, that has around about a 43% success rate. CPAP has 83%, massive gap. With our airway, it increases to 55, 56%, so that's the mandibular advancement plus the airway, still not at that 83% level. So we're introducing what's called, I suppose it's combination therapy. $2 component is added to the ductile of the appliance and it provides what's called EPAP. So it's this extra pressure on exhalation. This silicone valve at the back opens up on inhalation and then closes on exhalation. And the exhaled air passes through the small holes, building up pressure inside the airway. So in our clinical trials, our success rates have now actually moved to 67%. So we're getting there. That's coming to market in mid-October. And we're getting a lot of interest from sleep clinicians for that. Although it's a $2 component to make, we won't be selling it for that. It will be a lot more. Another product, so these are, and I should mention we're only using 3D printing here for those two stages. So nylon is a fantastic material for this prototyping stage. In fact, it's implantable, PA2200, great for evaluation, very strong. We're now moving to an injection molded version for the final product. That's for the valve housing. We now have in development, and this is part of our CRCP, a new product. This X-Vent is great for people that are nasal obstructors like me, because that extra pressure is just building up in the airway with just the oral airway, whereas my nose is blocked, and that's exhalation pressure comes from that. It's only about 50% of the population that have that sufficient nasal obstruction. The other 50% have patent nasal airways. And the key thing there is you have to keep the pressure in those individual patients as well. So that's both oral and nasal EPAP. And that's what we're calling here, OnePAP or oral nasal EPAP. And here we actually have nasal pillows on an extension to the device. The valve is now what's called a PEEP valve underneath that's adjustable between 2 and 20 centimetres of water. If you look at how a CPAP works, basically it's providing positive air pressure adjustable from 4 to 20 centimetres of water. We can basically provide CPAP therapy without about the pump and the hose, so it's like a CPAP in the pocket. Clinical results, I'm sure we're a public company, the results have been announced, so I'm happy to share it today. We're now up to 79% success rate in our clinical trial with the one PAP. We're nearly there. So we're hopeful with some tweaking that we'll be able to compete with the CPAP market, which is obviously a multi-billion-dollar market, for what are basically add-ons that improve our technology by a factor of 2. We then we're still at that 80% success rate. We also want to help those remaining 20%. How are we actually doing that? We're actually now providing combination therapy with CPAP just through the nose. So this is, we've got EPAP, we've got mandibular advancement, we've got our airway, and then low pressure CPAP through the nose. We found that patients that need, in another clinical trial at Europe, those that do need the CPAP only require about 30% of normal air pressures compared to CPAP delivered by a full face mask. So what's the upside for the patient? 30% of the pressures required. They don't have to wear a full face or Darth Vader mask. Still not that attractive, but better than having the disease. And this is for the people with very severe sleep apnea that might be having over 100 events per hour with O2 sats that get down to 50 or 60% at night. So this is our CRC that's only been going a bit over a year in collaboration with the CSIRO, Neuroscience out of Australia. This is this personalised approach to medicine. And it's, I suppose, goes hand in hand with CPAP because our devices are custom made, but we're not only customising the individual devices, we're now customising or personalising the actual type of therapy they're getting. And there's some longer term projects that we have planned there to actually develop an algorithm with the CSIRO so the patient, depending on their anatomical or non-anatomical inputs, so-called phenotyping, we can actually point the patient to a specific therapy from day one at the time of diagnosis. So I think the key message we've learned is that there's a lot more to medical device manufacturing than 3D printing. So that's the patient digital records. That can be either by taking impressions, pouring models and scanning in our lab. But there are these intraoral scanners now where dentists do in fact scan directly, chairside. There's then the CAD design. We have many of these developed over the years. We have proprietary software that's been developed in collaboration with CSIRO and Data61 to actually design the device. Once it's designed, it goes off to the cloud. It can be 3D printed anywhere. Could be in Melbourne, but we also started printing in other countries. There is then some post-printing in polishing, other manufacturing steps. It could be an insert manufacture for the titanium devices, and of course there's a whole lot of testing, a number of which we've actually performed in CSIRO. Is a bruxism simulation test using fatigue and compression simultaneously. Titanium can withstand a few thousand, it's probably 3,000 or 4,000 newtons. So we still have one or two patients break titanium, which is pretty interesting. And of course, then the finished product that gets shipped off to the patient, delivered through the dentist channel. So this is our sort of commercialisation pathway. I've done a number of startups in the time. This is, I suppose, a process that I've developed, and it's all around making sure that commercialisation process meets regulatory needs, but it's de-risking it as well. I won't go into a whole lot of detail, but this is sort of the pathway where we started. Dr. Hart came to me with a provisional patent. He'd done some research with a technology proof of concept on this acrylic handmade thing. That's when I got involved. We did a whole lot of work on the IP, commercial market analysis, end user market insight, did the more product proof of concept work over, it only took really 6 to 9 months to get good working versions in the collaboration collaboration with the CSIRO. We were actually on market. This was August 2013. We sold our first device in November 2014. So pretty rapid pathway to sales. I suppose the key thing there is, once again, it's a class 1 device, very low risk in Australia. And then we've moved on various iterations. There's probably 25 of each different product in improving it. And at the moment, we're just about finished what we think was 98% there, this design improvement. And it's all around this exponential increase in value, while also there's an exponential decrease in risk. That's what it's about, coming up with a business model and a commercial model that actually makes sense. So the challenges, I think for us, it is more of a consumer good, so the cost and speed of equipment is an issue. I mean, our RCAM machine is worth $1 million. It costs $60,000 a year to service it, whether we turn it on or not. Not a whole lot. I mean, it's about $6 worth of titanium in each one of those parts, but you have to have the labour. We have 2 people dedicated to run. They've got to get sick, they go on holidays. So if you look at the fixed costs, it becomes quite significant in running a 3D printer. I've looked at 3D printing facilities all around the world. There's really only, I think, 1 or 2 companies in Australia that actually can do it, and do it well, and it's because they have scale. In my view, you probably need 5, that's probably $2.5 million to $5 million worth of equipment, with only 2 people running those to actually make it cost effective. So it's pretty clear for us, having that one printer, it has done its job, if you like, from an R&D perspective, but for us to scale, do we want to spend investor funds on more 3D printers? And I think the answer is no. So we are, in fact, moving to a more outsourced model for 3D printing and using the existing facility for R&D. So what do we do with our existing equipment? So yeah, we want to keep that relationship. It's been fantastic with CSIRO over that last 5 years. The key thing when we looked at it is it's a certified facility, and there's only 3 in Australia, and we're the only ones with MedSAP, which is Medical Device Single Audit Program. So we can actually manufacture for FDA without having to worry about them inspecting us or an audit, and that's a massive asset. And it's all done in a very controlled process, full traceability, quality management system end to end. But it's a bit of a pain, but we've been audited through TÜV SÜD. It's quite an asset that we think Australia should take advantage of, and that's something that the CSIRO actually agrees with. So there's a CSIRO initiative that's being brought together. It's probably Stephan's the one to talk about, but I said I'd mention it. So what's this 3D printing consortium going to do? It's not around R&D. I mean, there's hundreds, if not thousands, of printers in Australia that can do great medical device prototyping, R&D. This is actually around medical device manufacturing. And there are only 3 accredited facilities in Australia. All 3 are part of this consortium, and it's around taking good ideas in medtech and commercialising them and manufacturing them in Australia. So the guys from the CSIRO have spoken to, I think there's 34 interested parties, with more and more being added by the day. There has been an initial sort of survey to understand what is the unmet need, and they're being separated into groups that are either investment ready or not. Do they want manufacturing contracting, or do they want other contractor services rather than just 3D printing? And the overwhelming response was it's all of those. So the consortium itself identified from the group that were interviewed that it's not just the 3D printing service. There's lots of those, even though this is accredited. There's a whole need around an R&D process. In CAD design, design software, post-processing, other components to build the medical device, and obviously testing to certified standards. So that's basically the product development process. In any of these, and it's pretty clear that a clinician either needs to be the champion of a medical device or be play a key role in the team. So there is a, if you like, matching process for those that don't have clinicians to make sure the device actually meets a clinical need, and market insight with customers, whether it's other clinicians. In our case, for instance, it would be patients as well. That's just the product. In medical device commercialisation, to have any chance of success, you have to have the other aspects. Now I'm talking about in larger scale, not just one-off products. This is around volume manufacturing on a global scale. You have to have an appropriate quality management system. It's got to be backed up with clinical trials to ISO 134, 155. You've got to have appropriate regulatory processes. It's very hard to convince regulators otherwise. They just tell you to go away. We have 3 FDA approvals, and they're not easy to get. Obviously, there's business planning strategy, sales and marketing, and go-to-market strategy, and of course funding as well. So all of those areas for medical device commercialisation. And this is exactly how Aventus started. We followed this process from start to finish. We're supported by other service providers from the legal and financial side, and of course IP management. Basically, we're just repeating Aventus, but numerous times through this model, and funding as well. So at the moment, there is a process going through those 34, figuring them out, which ones need to be incubated to get investment ready up to phase 2. We have some pretty significant investors interested in this to get to those that are at phase 2, but there's also some that are also on their way to glory separately, and we're quite happy to partner with them for the just contract and fee-for-service work. So that's happy to talk about Aventus, but the key people to contact with respect to this 3D printing consortium, the CSRO personnel, Rob Thomas, or Stefan is also here up front.
Thank you very much. And last but certainly not least, we have Dr. Anita Quigley, who completed a PhD in the Department of Medicine at the University of Melbourne. She is currently a research fellow at the University of Wollongong as part of an ARC Centre of Excellence, and is an honorary fellow at the Department of Medicine at the University of Melbourne. She's currently located at the new flagship BioFab 3D facilities at St Vincent's Hospital and in the Department of Clinical Neurosciences. And her current activities involve the use of human-induced pluripotent stem cells. Is that the abbreviation? Okay, good. For modelling of neurological disorders, development of biomaterials for tissue engineering, and 3D bioprinting. Again, numerous publications and a co-supervised number of PhDs. Please welcome her.
Okay, I guess my talk's going to be a little bit more different. It's going to be a little bit more biologically based. So I'm going to talk about some of the work we've been doing at the BioFab 3D Centre, which is located just up the road at St Vincent's Hospital. And there's been some talk tonight about 3D fabrication facilities located in hospitals, and I guess we are a 3D fabrication facility now located at St Vincent's Hospital in Melbourne. We are working with clinicians, a number of clinicians at the moment, and we're hoping to expand. And this is kind of, the BioFab Centre is kind of like a flagship centre for a much larger building that St Vincent's plus partner organisations, one of which is RMIT, are looking to get funded. They've nearly got all the money that they need to build the ACMD Medical Research Centre, and that's going to be very much focused on clinical solutions, integrating things like 3D bioprinting. Okay, so I won't keep you too long, as was just introduced before, so my area really when I started out in science was really neuroscience and cell molecular biology. Now I do a lot of IPS work looking at patient-derived stem cells for 3D printing solutions and tissue modelling of patient defects. Also do a lot of animal work as well, involving cell transplantation and tissue engineering. Now to do a lot of this work, obviously now we're looking at biomaterials. So I work with a lot of biodegradable polymers, hydrogels and conducting polymers. I started off as a biologist and now I've kind of had to become, I wouldn't call myself a fully fledged materials scientist, but I've certainly had to learn a lot about it to be able to work with materials scientists. And I think it's a real advantage to be interdisciplinary. And I've enjoyed the learning process too. So we do a lot of 3D printing. We also use other fabrication approaches or biofabrication approaches like wet spinning or galvanostatic deposition of conducting polymers to make conducting surfaces to influence cell behaviour. And as I mentioned before, all the work that we do is interdisciplinary. So I work with surgeons, material scientists, chemists, etc., to try and get the job done. So I'm involved in a research centre of excellence. That's part of it's run from the University of Wollongong. I'm located at BioFab, and basically the academic node that I'm actually involved with, including the University of Wollongong, is the University of Melbourne. So our work has resulted in quite a number of publications where our work is featured on the covers of various journals. So I guess if we're talking about the type of additive biomanufacturing that we do, it involves a number of different fields. So we look at materials development, in that we're actually trying to develop inks and biomaterials that are actually good for sustaining cell growth. Obviously, we do a lot of stem cell work and tissue engineering, as well as biofabrication that involves 3D printing and wet spinning, as I mentioned before. So some of the current projects that I'm working on include looking at 3D bioprinting and the formation of regenerative scaffolds. One of the projects I'm working on involves bioprinting and fabrication of functional 3D structures, involving looking at modelling brain activity using cells derived from patients with epilepsy or neurological disorders to try and actually mimic their brain activity in a dish. So we actually use 3D fabrication methods to create 3D structures where we can actually simulate we're trying to simulate what's going on in the brain in terms of neural network activity. So I work with with electrophysiologists as well as other biologists to do this work. So I work with Justin Burke, he's one of the electrophysiologists that I work with. I also work with people from RMIT. This is actually a picture of some neural cells derived from a patient. So we grew some iPS cells from the patient, and this is actually a hydrogel developed by Richard and Mitchell from RMIT. So it's a synthetic hydrogel that we've actually used to grow the neural cultures and have a look at the neural activity. So I'm also involved in work involving 3D cardiac patches as well. That's recently just started. So another project that we're looking at is interfacing with bionic and prosthetic devices. We've got a very good student. She's actually an orthopaedic trainee, so we have a lot of surgical students doing PhDs with us as well, which is kind of great. So she's looking at bioprinting functional skeletal muscle to develop neuroprosthetic interfaces. And I'll go into that in a little bit more detail later. And we'll also do a lot of work looking at making regenerative matrices containing stem cells to deliver stem cells in vitro, so in the body. And again, I'll go into that in a little bit more detail. So why do we want to fabricate things in 3D? Well, there are very big differences in the way that cells behave in 2D versus 3D. A lot of people, particularly in the stem cell field, are not growing things in a 2D culture dish anymore. They're actually using three-dimensional organoids. So the organoids basically spontaneously develop and tend to take on a lot of the characteristics of that particular organ or tissue that you're trying to mimic. So a lot of this work is actually done with iPS stem cells, which is kind of the biological area that I work in. And you actually see a lot more behavioural characteristics and function of these organoids that are native to the tissue of origin than you would see in 2D. So it's all about function and mimicking that function. So as an example, this is just a nice picture. These are some iPS-derived neurons growing on a multi-electrode array, and we actually measure the neurological or the electrical activity of these neurons from the patients. So we do that in 2D as well as 3D. Okay. So as an example of this is some work that we did with Justin. So he's the electrophysiologist in our group. We had a look at the neural activity of cultures. These cultures are actually from rat cortex. So this is just an electrophysiological readout of the electrical activity that's going on in this particular culture, and this is done on multi-electrode arrays. You can see there's lots of spiking and lots of neural activity going on here, and it's actually relatively disorganized. Whereas if you actually grow 3D primary neuronal cultures, we actually see brain-like activity in the dish in these cultures. So this type of organized network activity that you see here is actually the type of activity that you would see if you actually put electrodes on the surface of the skull. So it's a type of activity that you see in the brain. This is kind of the first time that this has been shown, and we're actually using this method for actually looking at patient neurological activity, so epileptic activity in patient-derived stem cells. So one of the things we're doing, and this is Catherine's muscle work, one of the things we're doing with the neural work is we're actually bioprinting 3D layers of the brain as well to try and mimic that activity in the different layers of the brain. So Catherine's work, as I mentioned before, involves 3D printing functional skeletal muscle. Obviously, it requires a lot of workup, so it really develops using specialised bioinks for the particular tissues that you want to print. You've got to have good printing fidelity to actually maintain the structure of the scaffold that you've created. So you've got to look at not only things like the material properties of the bioinks, but also the cell viability of the inks as well. And this is just a picture of some myoblasts that have been printed by Catherine, and the green dye is basically indicating the viable cells that are in that printed scaffold. So we get pretty good cell viability in our printed scaffolds. So in terms of function, basically what you're looking at here is one of these little areas here. So this little tubular area here that's part of the 3D printed structure. This is this little tubular area here. And you can see on the outside, the green staining is actually an axon stain, which stains the cytoplasm of the cell. We've got nice fibre formation on the outside of the bioprinted construct. And over on the right here, this is actually calcium imaging of muscle activity in that bioprinted construct. So she's actually been able to print functional skeletal muscle 3D constructs out for some of her work. So at the moment, she's it's going to take a while to go back. So at the moment, she's actually, even tonight, she's actually implanting some of these constructs in animal models to actually see if we can innovate these devices from the animal nerve supply and also vascularize the 3D printed constructs from the rat vascular supply as well. So their experiments are kind of ongoing at the moment. So another thing we do that I mentioned before is interfacing with prosthetic devices. So we've got another PhD student, Bijan, who's an engineer, and we've kind of thrown him in the deep end, and he's having to learn a lot of tissue culture, which he just loves. And so he's been doing a lot of muscle culture. No, he really does love it, really. And there's this picture up here just shows the muscle fibres that are grown in tissue culture here. So these muscle cells are from a mouse. This is actually the electrodes that you can see here of the multi-electrode array, and they're actually measuring the electrical activity of those muscle cells as they contract. Now we can feed this into a program. This is the work that Justin does. This is actually represents the activity that's going on the surface of the MEA, of the multi-electrode array, which each of these squares represents the activity of each electrode. So there's 64 squares there. And you can see the activity going from one side of the MEA to the other. So the muscle activity is actually going across in a wave. And what we've done, we've actually created algorithms where we can use this activity to control the movement of a robotic 3D printed prosthetic hand. So we're actually looking at using models like this. So eventually we're actually going to develop them obviously in vivo for use of prosthetic devices in humans. But we're looking at methods by which we can actually control prosthetic devices using peripheral muscles. Instead of having to have an implant in your head, you can actually have an implant in the peripheral muscle and actually control the prosthetic device that way, which is a little bit more user-friendly. Some of the other work we do is using 3D hydrogel scaffolds that have been fabricated either through 3D printing or through wet spinning to deliver stem cells and progenitor cells to various tissues. And you can't see it very well here, but this is actually the hind limb of a mouse in cross-section. And what we've done, we've created hydrogel scaffolds that have encapsulated muscle progenitor cells inside them. And we've implanted them inside the mouse. So the mouse model that we use is a naturally occurring disease model. It's got a disease called muscular dystrophy, which is it's exactly the same disease that humans get. So they have a mutation in the dystrophin gene. They have which is a gene that's really important for muscle function. So the cross-section of the muscle is this whole area here, and just from implanting one hydrogel implant, we can deliver muscle tissue or new muscle cells, which are these blue cells that you can see in this area there, to about 50% of the muscle, which is really a big area. So what people do now, and actually this is what's happening in clinical trials now, is people are actually directly injecting stem cells into the muscle, and you see nothing like this area of regeneration. So we're actually using hydrogels to enhance the cell delivery to muscle, and we're just about to publish this work. We've shown that this enhances the long-term delivery of cells in tissues, and it reduces the amount of fibrosis. You can see the fibrosis in this mouse muscle, which is in green, and this is the area where the cells are, so this is a serial section. It significantly reduces the amount of fibrosis that you see in the muscle as well in this disease model. So I'm involved in a lot of other projects that I'm not going to go into today, and I know we're kind of running a bit behind time, but I'd be really happy to speak to any of you about these projects. As I mentioned before, I'm working with someone from the University of Sydney on cardiac muscle myocardial patch, looking at development of novel bindings with some researchers from RMIT. Another project was started recently, and Carmen and Serena, who are in the audience, who are from BioFab as well, is looking at traces in 3D printed scaffolds. So I'm more interested in looking at neurological traces. They're actually working more in the cartilage field. I'm really embarrassed now. And we're also working on the BioPen project, which is involved with looking at cartilage regeneration. That's them there, Serena, Carmen, and Cahal, who's not in the audience tonight, are working on that project. And another project that we worked on as well is using additive fabrication and fabrication technologies to make a biodegradable nerve conduit that we published in the Journal of Neuroengineering a few years ago. And this work has continued. We've had further funding since to keep developing this model. So in summary, I've gone over a few projects. Sorry, it's been kind of like all thrown at you and I haven't been able to go into too much detail. I don't want to spend too long talking, but like I said, I'm happy to talk to anyone if anybody's interested in being involved in these projects. There's a lot of people involved in these projects that I'd like to thank, and please come and have a visit to the BioFab 3D Centre. I haven't actually brought any pictures of the types of printers that we've got there and the facilities that we've got there. But it's quite an exciting space because we've got a bioprinting room. We've got various printers that can create 3D models. We've got bioprinters, and I've got a high-end bioprinter at GSIM in a tissue culture laboratory. We've got bioreactors where we can actually develop the bioprinted scaffolds that we make outside of the body. And we've also got molecular biology room where we can do a lot of the molecular analysis that we need to do to interrogate the 3D printed models that we make sure that they're actually doing what we want them to do. So it's not just a room of bioprinters, there's actually a lot more involved as well. So I'd just like to thank everybody involved, and we've got a significant amount of our funding from MTP Connect, plus a few other foundations. So that's all. Thanks.
So the intent with tonight's event was to now get everyone up and have a bit of a panel discussion with all of the speakers. In the interest of time, we've only got 7 minutes before we're basically getting kicked out of the building. So I think we might have to turn this into sort of a two-part event, perhaps if we can manage to find a date where at least some, if not all of the speakers come back, or a similar event where we can come together and maybe have a bit of discussion and sort of talk about some of the things that were brought up today. But we have a quick round of applause and a big thank you to all of our speakers here today. modalities from the modelling and education, implants, more commercial applications and bioprinting. There was a lot of discussion that overlapped about the interdisciplinary work and the need to sort of wear multiple hats and have clinicians act like engineers and biologists act like engineers and engineers act like clinicians, but maybe not operate, everyone working together. So it was good to see that a lot of common ground between all the presenters tonight. I'd like to give again a big thank you to RMIT, to Jennifer and to Ivan for helping host and organise this event. We really appreciate both the venue and your assistance with this. I'd like to give a big thank you to my 3 volunteers that helped out today. Obviously we need to be out of here in about 5 minutes, so in the interim feel free to have that discussion amongst yourselves, and perhaps we can, for those that are interested, we can move to a venue nearby. And if anyone's got any feedback or suggestions for maybe what we could do for our next event, or how we could do things differently, if it's absolutely terrible, I'd love to hear that, and see you all on our next event. Thank you very much.